สัปดาห์ที่3แต่ก่อนจะไปสัปดาห์ที่3ต้องทำการบ้านให้เสร็จก่อน ยังไม่ผ่านผ่านหรือยัง ผ่านแล้วเหรอ ไม่ผ่านสิ ยังไม่ผ่าน มันยังมีควิซไม่ผ่านอยู่ นี่ไง ทำใหม่ โอเค อันนี้จำได้132นะ น่าจะไม่เปลี่ยนนะ132อันนี้180อันนี้เท่าไหร่วะ นับก็ได้นะ ก็จะเป็น เปิด Sam I am Sam I am Sam I am Sam I am โอ้เปลี่ยนอันนี้เนาะ Bennett กับ Bennett Gene Copy อันนี้ก็นับข้างบน2เนาะถ้ามันเป็น3ก็ต้องเป็น5ถูกไหม5อันนี้ก็ต้องเป็น6เป็น11แล้วก็อันนี้ก็จะต้องเป็นอันนี้เท่าไหร่อ่ะ6คูณ6คูณ6คูณ6ก็เป็นนี่เป็น3คูณ3คูณ3นั่นเป็น6คูณ6คูณ6ก็เป็น216ลบ36ก็ได้เป็น180บวกกับ6 186บวกกับ5 191นะนี่191อันนี้ a child cannot inherit an allele that is not present in either parent so there aren't as many degree of freedom here as there might be without the context specific information อันนี้นี่ก็จะมีอันนี้เนาะของพ่อของแม่อันนี้ก็จะเป็น2บวก2เป็น4อันนี้ก็เป็น1 2 3 4 5 6 9 4บวก9บวกอะไรอีกบวกอันนี้กับบวกอันนี้นะอันนี้เท่าไหร่3 6 9 9 2 18 18 2 3 6 49นะอันนี้อะไร decouple James and Lene James and Lene อันนี้ต้องใช้อันไหนนะ decouple ป่ะ decouple non decouple กับ decouple คืออันไหนวะอันนี้นะ decouple อันนี้ออกไปก่อนmode Curie mode เจมส์เลเน่อยากจะเลี้ยงจะรับลูกมาเลี้ยงหรือจะเลี้ยงลูกหรือจะมีลูกเองโดยที่ทั้ง2คนเนี่ยมี F ใหญ่ ทั้งสองคนไม่มีใครเป็น cystic fibrosis เจมส์กับเรเน่อยู่ไหนนี่ไม่มีใครเป็นเจมส์ไม่เป็นมีหนึ่งอันก็ได้เป็น0.4672อันนี้ทำได้เป็น m กำลัง2n ถูกไหมอันนี้เป็น mn อันนี้อ่ะ AB independent แน่ๆถูกแน่ๆนี่รู้อีกอันหนึ่ง independent อันนี้ถูกแน่ๆแล้วอีกอันหนึ่ง when only A1 B2 or A2 B1 if the person has otherwise the person doesn't have เป็นไปได้ไหมลองเขียนดูสิ A1 B2 เป็น A2 B1 เป็นมันไม่ได้สิ neither gene A nor gene B contribute to SMA 0000เนี่ย A1 B1 make a person more likely to be have SMA when both these alleles A1 B1 make person more likely to have SMA when both of these alleles are present but neither affect SMA ไม่ได้เนาะอันนี้ต้องเป็นแบบพวกอะไรอะ deterministic and อะไรอย่างงี้เนาะ gene A contribute to SMA but gene B does not contribute to SMA allele A allele B1 A1 B1 ทำให้ equally make person equally more likely to have SMA ก็คือแบบมีโอเมก้าเท่ากันโอเมก้า1 A กับ1 B but when both are present the effect is the same ไม่น่าใช่นะเนี่ยมันไม่น่าจะได้ต้องบวกเข้าไปอีกอันนี้ไม่ได้แน่ๆที่เหลือล่ะ B ไม่ส่งผลต่อ SMA อาจจะส่งผลต่อโรคอื่นนะแล้วก็จะไม่ส่งผลต่อ effect of gene A on SMA อันนี้ถูกเพราะมัน independent ถูกไหมอันนี้ผิดแน่ๆผิดแน่ๆ neither gene A gene B contribute to SMA โอเมก้าเป็น0แล้วมันจะมีทำไมใช่ไหมเอาเรียก N1 B1 make person more likely to have SMA บวกโอเมก้าเข้าไปฮะไม่ได้มันก็ต้องส่งผล neither ไม่ได้ใช่ไหมมันต้องส่งผลนี่ส่งผลนี่ส่งผลนี่ต้องส่งผลอันนี้อะไรอ่ะอุ้ยลืมแล้วอ่ะ1 2 3ป่ะน่าจะไม่ผิดคุ้นๆว่า1 2 3นะอันนี้ Bayesian no longer interested in finding out whether his father เป็นไหมเราไม่รู้ no longer interested ไม่อยากรู้ด้วยว่าพ่อเป็นไหมเจมมาหาด้วยคำถามอีกอันหนึ่ง ว่า did his father have SMA เป็นไหมถามว่าพ่อเป็นไหมเขาและโรบินเป็นอะไรวะ ไม่สนใจแล้ว no longer interested in finding out whether his father had STF ไม่สนใจอีกต่อไป with another question did his father อะไรวะตกลงมันอยากสนใจหรือไม่สนใจก็คือคำถามก็คือว่าอีล่าเป็นไหมถ้าเขาและโรบินเป็นใช่ไหมอีล่าเป็นไหมถ้าเขาและโรบินเป็นเจมส์เป็นโรบินอยู่ไหนโรบินเป็นอีล่าเนี่ยอีล่าเป็นไหมโรบินเป็นเขาเป็นอีล่าคือ4246อ๋อนี่คนละโลกกันนี่แบบว่าไม่สนใจแล้วว่าเป็นซิสติกไฟโบซิสไหมแต่ว่าสนว่าเป็น SMA ไหมอันนี้คือ SMA นี่ SMA ป่าวะเอาในซิสติกไฟโบซิสผิดโลกผิดโลกต้องเปิด SMA เป็นหลายโลกอะเนี่ยเป็นหลายโลกปิดไปโอ้ยคอมเปิดเยอะไปนะนี่อ๋ออันนี้ต้องเป็นอันนี้นะ SMA เขาและโรบินเป็น SMA ถามว่าพ่อเป็น SMA ไหมโหมดคิวรี่โหมดคิวรี่โชว์เอาเขาคือเจมส์เนาะเป็นโรบินเป็นพ่อเป็นไหมเป็น35413541โอเคครบแล้วนะไม่รู้ถูกผิดขนาดไหนเรามาดูกันหวังว่าจะผ่านอ้าวผ่านแล้วแต่มีผิดอยู่ผิดข้อนี้นะ decouple ยังหาคำตอบที่ถูกต้องไม่ได้ที่เหลือถูกหมดแล้วเดี๋ยวต้องไปหาคำตอบกันว่าพารามิเตอร์ที่ใช้สำหรับ decouple เนี่ยมันเท่าไหร่สำหรับ3 allele มีคำใบ้ด้วยว่า child เนี่ย cannot inherit allele that is not present in คือถ้า child ไม่สามารถจะ inherit allele ได้ถ้าไม่เจอใน either parent อ๋อเก็ตละนะมันก็ต้องน้อยลงไปอีกถูกไหมแป๊บนึงนะเหมือนอันนี้ปิดก่อนอันนี้นี่คือ child 2อันนี้นะ child มันจะต้องมีแค่ f ต้องมีแค่อันใดอันหนึ่งนะ f หรือ f ใหญ่ f ใหญ่ f ใหญ่ f ใหญ่ f เล็ก f ใหญ่ f เล็ก n ไม่มีเห็นไหมแต่ถ้า n ไม่มีมันจะเหลือแค่8เองอะเหลือ8 88922จดคำตอบของอันอื่นไว้ก่อนเราจะได้มาแก้ในทีหลังเพื่อให้ได้อัน132 132180109หวังว่าจะไม่เปลี่ยนข้อสอบนี้จะต้องแก้เป็นเท่าไหร่นะ29น้อยจังเลยข้อนี้เหลือข้อนี้ข้อเดียวที่ตอบไม่ได้สักทีไปบทต่อมานะฮะบทที่3วันนี้จะดูหรือ text 8 ชั่วโมงใช้เวลา8 ชั่วโมงเลยเหรอ yes helpful ตอนนี้ใช้ชั่วโมงเดียวก็น่าจบแล้วไหมไม่จบ2 ชั่วโมงอ่ะจบทั้งหมดเนี้ยแต่อันเนี้ยน่าจะนาน pairwise Markov network general gift distribution conditional random fields no clue มากๆเลยเขียนอะไรมา I have no clue เตรียมสมุดจดไว้ให้ดี pairwise Markov network general gift distribution แล้วก็ conditional random field ไม่รู้เรื่องเลยนะครับผมแต่ละอย่างแต่ละอันคืออะไรบ้าง เดี๋ยวเราลองโหลดไม่ใช่โหลดเอาไฟล์มาใช้ก่อนเรายังไม่ได้เอาไฟล์ที่เราโหลดมาสำหรับตัวบทเรียนมาใช้เนาะจะได้เอามาช่วยจดได้เอาทั้งหมดนี้เลยเนาะทีมทีมตัวเองนะฮะแล้วเราก็โหลดมา
So as we said at the very beginning, there's two main families of graphical models. There's those that are based on directed graphs, directed acyclic graphs, and those that are based on undirected graphs. The undirected graphical models are typically called Markov networks. They're also called Markov random fields. We're going to start by talking about the simplest subclass of those, which is pairwise Markov networks, and then we're going to generalize it. So let's look again at a toy example just to illustrate what's going on. This is an example of 4 people who are studying together in study pairs. And notice that Alice and Charles don't get along, and Bob and Debbie had a bad breakup, so they don't talk to each other either. And so really, we only have the study pairs that are marked by the edges on this diagram. And and the random variables here indicate whether the students have a particular misconception, because the material was a little confusing. So the random variable says, does the student have a misconception or not? This particular misconception. And the intuition here says that if 2 students study together, then they kind of influence each other. And so we have, so for example, if Alice and Bob study together, then this edge indicates that if one of them has the misconception, the other one's likely to have the misconception. Now, this doesn't fit neatly into the purview of a directed graph, because the influence flows in both directions. And so you can't really point an arrow from Alice to Bob or from Bob to Alice. And so we're going to use an undirected graph to represent this. So that's great, but how do you parameterize an undirected graph? Because you no longer have the notion of a conditional probability distribution, because there's no variable that's conditioning and one that you condition on. And so how do we do this? So we're going to use the general notion of a factor, which we defined previously. And notice that this really is a general factor in that the numbers don't even, are not even within the range 0, 1. Now, what do these factors mean? These factors have many names. They're called affinity functions or compatibility functions. They're also called soft constraints in different settings. So what these numbers mean is the local happiness of the variables A and B to take a particular joint assignment. So here we have that, we can see that the happiest assignment, as far as A and B are concerned, in isolation of everything else, is A0, B0. Okay, this is the case where neither student has the misconception. That's the happy assignment. We see that the second happiest assignment is A1, B1, where, again, the students agree. And in this case, they both have the misconception. And finally, the other 2 in the middle are the least happy of all. Now, this is a local happiness, and we have similar notions of happiness for the other pairs in the graph. So in this case, we see not only that there is a strong sentiment in favor of agreement, it's much stronger than in the A-B case. So B and C really like to agree with each other. They, it's very difficult for them to have opposing opinions. Okay? On the other hand, Charles and Debbie like to argue with each other all the time. And so if one of them says that it's going to rain today, the other one's going to say that it's sunny today. And so really, you can see that the preferred assignments for their local opinion is the ones that they disagree with each other. Okay? And again, A and D like to agree. So this is sort of describing the overall state by a bunch of little pieces. And how are we going to put these pieces together to define a joint probability distribution? We are going to use the notion of product of factors. And so here we are, and we're going to take all these factors and we're going to multiply them together. That's great. except that this is in no way, shape, or form a probability distribution because its numbers aren't even in the interval 0, 1, which is why you'll notice there's a little tilde on top of the p. This tilde normalized measure. Okay? So how do we turn an unnormalized measure into a probability distribution? Well, we normalize it. Well, actually, sorry. Before that, here is the unnormalized measure, so you can see it here, just to sort of highlight the point. How do we turn this unnormalized measure into a probability distribution? We normalize it, and that normalization here has a name. It's called the partition function for historical reasons that come from its origins in statistical physics, and I'm not even going to describe why it's called that, but that's what it's called. But you can think of it simply as the normalizing constant that is going to make all of these sum to 1. So we're going to get it by simply summing up all these entries, and that's going to give us the value z. And if we divide all of these entries by z, we get a normalized probability distribution, and that is the probability distribution that's defined by this graph. So now let's think about what these factors mean. And let's think about this factor phi1 of AB, which is this local happiness between A and B. And let's think about how it relates to the probability distribution. So we might think that this is the marginal probability of A and B in the joint distribution. Or maybe it's the conditional distribution of A given B, or maybe B given A. Or maybe it's the joint probability of A and B given C or D. The answer is, it's none of the above. So let's go back and look at what this actually means in this particular context. So here we have the set of factors that we use to construct this distribution. And here, trust me, is the marginal probability of A and B as defined by the set of factors phi. I'm going to use a little phi here to denote the fact that it was derived from the set of factors phi equals phi1 phi. Oh, come on. Or no. Try it again. Phi1, 2, phi 3. Okay? So let's compare this distribution to the factor phi1. We can see that not only does it not respect the fact that A and B like to agree with each other, here A and B like to agree with each other by a lot. I mean, remember this is 3 times higher than the next highest value. Here, that probability has 0.13, and the other high value assignment on this side, the one that had 10, has only 0.04. What is the single highest assignment here? It's this one. Let's think about why that is. This probability distribution is constructed by multiplying all 4 of these factors. And if you think about what's going on here, you see that B really, really likes to agree with C. So these guys are really closely tied together. And actually, this should probably be. And A and D similarly like to agree. So these are really, really closely tied together. These guys, C and D, strongly like to disagree. They like to have opposite values. Now, all 3 of these factors are actually stronger. That is, the differences between the assignments are bigger than in phi1. So where are you going to break the cycle? You can't have D agreeing with A agreeing with B agreeing with C, and C disagreeing with D. It doesn't work. And so somewhere this cycle has to be, this loop has to be broken, and the place where it gets broken is A and B because that's a weaker factor. So the AB probability is actually some kind of complicated aggregate of these different factors that are used to compose the Markov network. Each other. Here, A and B like to agree with each other by a lot. I mean, remember this is 3 times higher than the next highest value. Here, that probability has 0.13, and the other high value assignment on this side, the one that had 10, has only 0.04. What is the single highest assignment here? It's this one. Let's think about why that is. This probability distribution is constructed by multiplying all 4 of these factors. And if you think about what's going on here, you see that B really, really likes to agree with C. So these guys are really closely tied together. And actually, this should probably be. And A and D similarly like to agree. So these are really, really closely tied together. These guys, C and D, strongly like to disagree. They like to have opposite values. Now, all 3 of these factors are actually stronger. That is, the differences between the assignments are bigger than in phi 1. So where are you going to break the cycle? You can't have D agreeing with A agreeing with B agreeing with C, and C disagreeing with D. It doesn't work. And so somewhere the cycle has to be, this loop has to be broken, and the place where it gets broken is A and B because that's a weaker factor. So the AB probability is actually some kind of complicated aggregate of these different factors that are used to compose the Markov network. And this is actually an important point because it is going to come back and haunt us in later parts of the course. There isn't a natural mapping between the probability distribution and the factors that are used to compose it. You can't look at the probability distribution and say, aha, this piece of it is what phi 1 ought to be. This is in direct contrast to Bayesian network where the factors were all conditional probabilities and you could just look at the distribution and compute them. Here you can't do that. And that actually turns out to affect things like how we can learn these factors from data because you can't just extract them directly from the probability distribution. So with that definition, with that intuition, we can now go ahead and define a pairwise Markov network. And I'm defining it explicitly because pairwise Markov networks are sufficiently commonly used as a class of general Markov networks that it's worth giving them their own place. So a pairwise Markov network is an undirected graph whose nodes are the random variables, x1 up to xn. And we have edges, xi, connecting to xj. And each one of them is associated with a factor, also known as a potential, phi ij, xij. Okay? That's what, this shouldn't be an edge, this should be a comma. That's a pairwise Markov network. And from that, and here's an example of a slightly larger Markov network. This is a Markov network that is in the form of a grid. This is the kind of network that's used, for example, when we're doing various operations on images, because then the variables correspond to pixels, for example. And this is the Markov network that corresponds to the image segmentation when we're using superpixels, in which case it's no longer a regular grid. So we've previously seen the notion of pairwise Markov networks. But now we're going to define a much more general notion that is considerably more expressive than the pairwise case. And that definition is called a Gibbs distribution. So in order to motivate the notion of a Gibbs distribution, let's look at the most expressive Markov network that we could possibly define in the context of pairwise interactions. So here we have 4 random variables, A, B, C, D, and I've introduced all of the possible pairwise edges between them. And so the question is that we'd like to ask ourselves is this good enough? So is this fully expressive? Or in other words, can it represent any probability distribution over 4 random variables. So one way to convince ourselves of whether it can or can't is to go and do the general case and just look at, or in other words, can it represent any probability distribution over 4 random variables? So one way to convince ourselves of whether it can or can't is to go and do the general case and just look at a little bit of asymptotics. So consider a fully connected pairwise Markov network over n random variables, and let's assume that each variable xi has d values. How many parameters does the network have? And for the moment, let's just focus on pairwise interactions. On just the pairwise potentials. Let's ignore the potentials associated with singleton nodes. So let's do a little bit of analysis. If we have n variables, how many edges are there in the network? How many parameters per edge? So the total number of parameters in a fully connected pairwise Markov network is O of n squared times d squared. Great. Can we represent any probability distribution using O of n squared times d squared parameters? How many parameters are there in a general probability distribution over n random variables where each has d values? How many free parameters do we have? Well, this is much, much bigger than that. Which means that if, well, this is much, are there in a general probability distribution, or present any probability distribution using O of n squared times d squared parameters? How many parameters are there in a general probability distribution over n random variables where each has d values? How many free parameters do we have? Well, this is much, much bigger than that. Which means that if you just even think about it intuitively without getting into formal arguments, pairwise Markov networks are not sufficiently expressive to capture all probability distributions. So how do we increase the coverage of this undirected representation? We need to move away from pairwise edges. So in order to parameterize what we call a general Gibbs distribution, we're going to parameterize it using general factors, each of which has a scope that might contain more than 2 variables. So whereas before we just had factors over pairs, now we have factors over triplets, quadruplets, and anything else. Can we now represent every probability distribution? Well, sure, because we can have a factor over all n variables together, and by, that immediately defines, allows us to define a general probability distribution. In fact, we even said that a probability distribution is a factor whose scope is x1 up to xn. So in order to define this general framework more formally, a Gibbs distribution is parameterized by a set of factors phi. And we're going to define this distribution in 2 steps, 3 steps even. The first thing we're going to do, just like in the case of pairwise Markov networks, is we're going to take all of the factors, so here we have k factors, and we're going to multiply them. And this is just the familiar operation of factor product, which we've seen in multiple contexts before. Now, this is perfectly fine, but the problem is that this is not necessarily a probability distribution. In fact, it almost never will be a probability distribution because we have put no constraints on the factors. And so that's why we have this tilde here that highlights the fact that this is what we called previously an unnormalized measure. And so if we want to turn the unnormalized measure into a probability distribution, just like in the pairwise case, we're going to define what's called a partition function, which is just the normalizing constant, which we get by summing up over all possible assignments the variable x1 up to xn. That partition function can then be used to divide all of the entries in the unnormalized measure to give us, something that shouldn't have a tilde on it, but rather is a probability distribution P sub phi of x1 up to xn. Now, that was just a definition of the distribution in terms of a set of parameters. Where's the Markov network in all this? So let's think about what is the Markov network that we would like to have for a Gibbs distribution with a certain set of factors phi. So in order to get the intuition, let's look at a distribution that involves 2 factors, phi1, whose scope is A, B, and C, and phi2, whose scope is B, C, and D. And so I'm going to use a different color for phi2. So what edges should the Markov network have when we wanted to encode the fact that A, B, and C all get to interact with each other together? And intuitively, what we'd then like to have is a network that has an edge from A and B, an edge between B and C, and an edge between A and C. Okay? Because that captures the fact that there's direct probabilistic relationships between all of them. What about the other one? Here we have between B and C, C and D, and B and D. And this is the induced Markov network in this particular case. More generally, if we have a set of factors phi, each of which has where each phi I has, this is the induced Markov network in this particular case. More generally, if we have a set of factors phi, each of which has where each phi I has a particular scope di, the induced Markov network, which we're going to call h sub phi, has an edge between a pair of variables xi and xj whenever there exists a factor phi I in phi such that, phi in phi such that xi, comma xj are both in the scope of the factor phi m. That is, two variables are connected whenever they appear together in the same scope. Now we can go ahead and turn this around and define the notion, just like we had for Bayesian network, of when a probability distribution P factorizes over a graph H. That is, at what point can I represent P over a particular graph H? And this basically asks the question of, is there a set of parameters phi that are going to let me represent the probability P? So this is just a straightforward going through the definition that we had before. Does there exist a phi such that P is equal to P of phi, where P of phi is defined as we defined previously as a normalized product of factors? And such that H is the induced graph for the set of factors phi. So P factorizes over H if there exists a set of factors phi, such that I can represent P using those factors, and H is the induced graph for that set of factors. So that's when I can encode a distribution P over a graph H. So now let's ask ourselves the question. If you give me a graph H, can I tell you what the factorization of a distribution P over that graph would be? That is, which is the representation of the distribution that I had in mind when I drew this graph? So here we have this graph over A, B, C, and D, and which Gibbs distribution would induce the graph? graph H? Well, let's look at them one at a time. So here we have phi 1 of ABD and phi 2 of BCD. And we see that there is an edge, indeed, between A and B, B and A and D, and conversely, between B and C, B and D, and C and D. So the answer here is yes. This distribution would induce this set of factors would induce this graph. Okay, what about the next one? This? And ask yourself the same question. Well, phi 1 of AB would induce this edge. BC, yep. CD, yep. AD, and BD. Well, here's another distribution with a different set of factors that induces the exact same graph. The third one is the same principle. We have the edges ABD, AB, BD, and AD, and then we have BC and CD. So here's another distribution that induces the exact same graph. What that tells us is that we cannot, and this is important, cannot read the factorization from the graph. That is, we have different factorizations that are quite different in their expressive power, all of which induce the exact same graph. And we've already seen an example of that. When we had the fully connected pairwise Markov network, we had one parameterization that had O of n squared d squared parameters. We had another parameterization that had a full factor over all n variables, so it had d to the n parameters. And these are two very different representations with very different expressive power that nevertheless induce the exact same graph. Which brings us to the question of why then is the graph the same? What does the graph really tell us, given that it's not telling us the structure of the factorization? So going back to the example on the previous slide, we have these two factorizations, one of which use triplet factors and the second one uses pairwise factors. And let's think about what is the flow of influence in these factors. So when can one variable influence another? And we can see, and we think about this intuitively, when can B influence D? Is this different in the two graphs, in the two distributions? And the answer is, well, not really. I mean, once we have a factor, here in this case it's phi 1, in this case it's phi 5, that ties B and D directly, then the fact is that B can influence D. What about can A influence C? Well, so can A influence C? A can influence C via D by going through, in this case, the ABD factor, and then subsequently utilizing the dependencies within the BCD factor. And in this case, it can use the AD factor and then the CD factor. And so the point is, although the parameterization of the two distributions are different, the paths in the graph, the trails in the graph through which influence can flow, is the same regardless of this finer grained structure of the factorization. That ties B and D directly, then the fact is that B can influence D. By going through, can A influence C? Well, so can A influence C? A can influence C via D by going through, in this case, the ABD factor, and then subsequently utilizing the dependencies within the BCD factor. And in this case, it can use the AD factor and then the CD factor. And so the point is, although the parameterization of the two distributions are different, the paths in the graph, the trails in the graph through which influence can flow, is the same regardless of this finer grained structure of the factorization, which is why the graphs in those two cases are the same. So let's formalize this definition. We're going to define the notion of an active trail in a Markov network. And this is actually a very simple definition. It's much simpler than the analogous definition in the context of Bayesian network. We have that a trail going from x1 up to xn is active given a set of observed variables z if basically no xi along the trail is in z. Because an active trail only flows through variables that are unobserved. Once we observe a variable along the trail, influence kind of stops because that variable is now set, and so you can't really influence it, and if you can't influence it, you can't influence anything subsequently along that path. So for example, the trail from B to D is active, so this is active, but not if A is observed. So once I observe A, I can no longer influence, B can no longer influence D if I So to summarize, we define the notion of a Gibbs distribution, which represents a distribution P as a normalized product of factors, specify the factorization of P, the justification for why the graphs for different factorizations are the same, because the active trails in a graph depend only on the graph.
เมื่อกี้มันเป็น V structure ก็คือว่าถ้า ถ้าเป็นตัว active trail ของ Markov ถ้าเป็น active trail ของ Markov เนี่ยมันจะไม่มีทิศทางใช่ไหมอย่างเช่น x y ข้างล่างคือ c เป็น V structure ถ้ามันเป็นมีทิศทางแบบ Bayesian network เนี่ยถ้า c ถูก activate เนี่ยมันจะกลายเป็นว่า x ส่งผลต่อ y ได้หรือ y ส่งผลต่อ x ได้แต่ว่าถ้า c ใน Markov network ที่เป็น undirected graph เนี่ย x กับ y เนี่ยมันจะเหมือนไม่มีทิศทางมันก็เป็นเส้นเลือกเชื่อมกันเพราะถ้า c มันถูก activate c มันถูก observe เนี่ยมันก็จะทำให้มันบล็อก x กับ y อันนี้ descendant แปลว่าลูกเนี่ย ancestor แปลว่า parent
Use Markov network which connects every pair of nodes that are in the same factor. And the motivation, and although we noted that the Markov network structure doesn't fully specify the factorization of P, the justification for why the graphs for different factorizations are the same, because the active trails in a graph depend only on the graph structure.